Okay, so we're going to look at a second little look at implicit differentiation, but I would like to look at the second derivative here and emphasize that within this video. And I decided to start with a really, really simple question and then go to one that's a little bit harder to handle. So let's take off from here. This is a little problem we studied last year. Now, when we write it this way, it looks kind of like how we would generally approach it in a calculus class. But if we would divide everything here by the number 16, this is actually what we looked at last year in math analysis. This is a simple hyperbola. Notice that there's nothing attached to x or y here, so that hyperbola is centered at 0, 0. What we did last year is we would take the square root of both, the x and the y value. I'd go over 4, back 4, 1, 2, 3, 4. I'd go up 2 and down 2. I think when I get to this next spot, you might remember we made a box out of this thing. Then we took a second to draw in some asymptotes. I don't know if this is starting to ring a bell here with you, but we drew in some asymptotes. Like this through the corners of the box. And then we ended up drawing our hyperbola looking like this. Now, what you can see, the reason I thought it would be worthwhile to kind of go through that process is sometimes it's nice when somebody asks you a question to at least kind of know a little bit about what you would anticipate. So one of the things that I would anticipate in this problem is that there are no horizontal tangents. This thing never becomes flat. It just doesn't. And in fact, when you look at it, my rise is 2 and my run is 4. So the slope of this is 1/2 x. The slope of this one is -1/2 x. Of course, its y-intercept is 0. So as you go towards infinity, the slopes get closer and closer to either +1/2 or -1/2 is kind of how that's going to work out. So we might kind of see a little evidence of that as well. So anyway, let's see what goes on. And the vertical asymptotes should happen here at these two values at 4, 0 and -4, 0 should be vertical, okay? So let's see what happens. Let's take our first derivative. So the derivative would be 2x. The derivative of this guy right here would be -8y times dy dx. And of course, the derivative of 16 is 0. Take another quickie little movement of stuff around. We're going to move the 2x to the other side, and therefore dy dx is what happens when we divide both sides by -8y, which is going to give me +x over 4y is what I just got. Now, as it turns out, if that is true right there, that is my derivative, so where would then there be a, say, vertical asymptote would happen when the denominator is 0. So notice the denominator would be 0 if 4y is 0. Now, if 4 times y is 0, we could plug that back into the original problem, meaning, of course, y itself is 0, and I'd have x squared minus 0, because y was 0, is 16, and that gave me x squared is 16, or x equals plus and minus 4, which you'll see evidence of here. Now, the other part would be where would there be a horizontal tangent? Now, that's assuming we don't have this picture and we don't realize that there is no such thing. That would happen when the numerator is 0. So what would happen if we made the numerator x 0? Now, if you made x 0 and you plugged it back into the original problem, if you plug that in, you'd have 0 minus 4y squared equals 16, which means we could divide both sides by -4, and you get y squared equals -4, and we can very quickly see that that would be an imaginary value. So pretty quick. Now, the part that I wanted to hit in this video more significantly is this next portion. I want to talk about what is d squared y dx squared. In other words, what is the derivative of this derivative? So this is the first version. I'll try to go fairly slow. So if I already have the first derivative, then the second derivative is just the derivative of this guy. So we've got a quotient, and I will do that. Let's do a low d high, which of course is 1, minus high d low. Now d low would be 4y prime, or 4 dy dx's, all over the square of what's below. Now, that doesn't seem like that big of a deal, but we do have a little something we should do now. Because we have 4y minus 4x. We have this 16y squared, but this dy dx that is sitting right there, we already know what dy dx is. We just found it right here. So we're supposed to replace that with x over 4y. So I suppose the only thing that would make sense to do, just to clean it up a little teeny bit more, is why don't we go ahead and multiply the numerator and the denominator by a fraction buster to make it a little bit nicer for y. And therefore, I would say d squared y dx squared, also known as y double prime. If we did that, we would get 16y squared. I did that so these would cancel out, minus 4x squared over 16y squared. I suppose we could divide everything by 4 now. And I guess we're good. That's it. Pretty cool. All right. That's all that I wanted to do with that particular problem. Now, my second question is not too much harder. I just kind of made one up. I had xy plus y squared equals 4x. Now, that is not a particularly complicated one, but I suppose if we were to look at a quick Desmos window, we might see that this one is a little weird as far as a graph goes. So let's go ahead and see that graph, because I can't tell you what this one looks like as well, because it's just kind of a new one. We've got this crazy shape that looks almost like a hyperbola, but it's been turned to the side. It's kind of weird. So anyway, let's just see what happens when we go and attack this guy. So we've got a start with a product rule. The derivative of the first times the second. So the derivative of the first is 1 times the second, which is y, plus the derivative of the second, dy dx, times the first. Then we got our chain rule here. It is 2 times y times the derivative of the inside of this, which of course is dy dx, equals 4. Now, just like the previous problem, we wanted to bring together everything that has a dy dx, which we have two different pieces here. There's an x and a 2y right here. And everything that does not have a dy dx should be on the other side. So all I need to do is move that y across. So no huge deal right now. So I now know that dy dx is 4 minus y over x plus 2y. Now, what I wanted to do is two little things with that. First is reiterate something that I keep kind of trying to push at, is where was that vertical tangent? Now that vertical tangent, of course, happens quite nicely when x plus 2y is 0, or in other words, where x is the same as negative 2y. Now again, you can do this in any variety that you want, but since I have two variables and I can write one in terms of the other, I could go ahead and simplify it. So what I'm going to do is I'm going to take all of these x's over here, and I'm going to replace them with negative 2y. So I've got negative 2y times y plus y squared equals 4 times negative 2y. Because I know that vertical tangent would happen wherever that's true. So I've got negative 2y squared plus y squared equals negative 8y. Little cleanup, negative y squared is negative 8y. I'm going to move the y to the other side, and we end up with a fairly benign story, which, if you factor it, you can see very quickly that that's going to happen when y is either 0 or when y is 8. And of course, if I know that y is 0, then I know that x is 0. And if I know that y is 8, I know that x is negative 16. So let's go ahead and take a quick look at Desmos to see how we did. So we found one of our vertical tangents right here at negative 16.8, and we found the other one at 0, 0. So you can see a quick confirmation of that. Now, as it turns out, you can tell on this graph that there is no horizontal tangent. So I debated about whether I should show that to you or not, because I don't want the videos to be too long. But of course, if we wanted to take the original equation and set it equal to 0, all we would do is we would take 4 minus y and set that to 0. So I would have 4 equals y. Now, that doesn't sound that bad. So if I just come to the original problem and I replace everywhere that I had a y with a number 4, I would have 4x. I'd have y squared, which is 16. And over here, I'd have 4x. So if I subtracted 4x from both sides, I get 16 equals 0. Well, we said there was no answer where there was a horizontal tangent. So this basically assumes, as soon as I do that, I assume that there is a place where this happens. So if I assume there is a horizontal tangent, then I must assume also that 16 and 0 are the same place. So I had to have been wrong when I assumed that this place existed. So there is no horizontal tangent. But to finish my story up, I had dy dx. Now here's where the problem gets tough. So I'm going to go ahead and do this one time on this video. I don't know that I'm going to make a lot of videos with this, but I want to try to find that y double prime. So I'm going to go ahead and take the derivative of this. Now, again, that doesn't sound like it should be all that hard, but as a hint, I'm going to kind of blow this thing up a little bit. So I'm going to do my low d high. So keep in mind the derivative of this is 0, the derivative of this is dy dx. Minus high d low. Now the d low is a 1 plus 2 dy dx's over the square of what's below. Now, at first glance, that doesn't look too bad, but we have a little bit of work that we need to do there. So I decided that I thought it would be beneficial for me to distribute this out so I could at least clean it up a little bit. And I think what I'm going to do is I'm going to adopt for the time being, everywhere I see a dy dx for brevity, I'm going to use y prime and I'm going to highlight that, okay? So what I have is on the top, I'm going to go ahead and write this down so I don't forget. So I have negative x y prime, right? Minus 2y times y prime. And that gives me the first piece. Now over here, it's a little bit harder. If I distribute the negative 4 times the 1, I've got a minus 4. The negative 4 times this is going to be a negative 8y prime. And then I've got a positive y times 1. And then I have a negative 2y. I got to be careful. I've got a positive y times 2. So I got a 2y times y prime. Okay. So notice that I have a variety of y primes kicking throughout this problem. So my next value, y double prime, is I had my y, I had my minus 4, and then I have a whole bunch of these pieces in here. I've got a negative x, I have a negative 2y, I have a negative 8, and I have a 2y that all have a y prime involved in them. And so the only thing that I would say then is if at this moment in time we replace that y prime with my original y prime, which you had over here, I could honestly say that technically I'm done with that problem, but that's really kind of frowned upon to leave a fraction buried in a fraction. So we're going to do one last little step right here, and we're going to multiply the top and bottom by x plus 2y to clean it up just a little teeny bit. And in doing so, we have y double prime, also known as d squared y dx squared. In the denominator, we have now x plus 2y to the third, because we multiplied an extra one in here. Again, on this portion over here, the dy dx's, those would cancel, right? And so I still have my x, my 2y, my 8, my 2y, and my 4 minus y. But over here, when this distributes to this portion, I still then have my y minus 4, and it's going to then be multiplied by x plus 2y. And I suppose I could then maybe multiply this out and see if I could simplify it. But, you know, when these problems get really, really long, sometimes you have to find a place where we're going to choose to stop. But there are some things that you would see if you were to multiply them out. You see there's like a negative 4x here. We have a negative 4x. We have some like terms that we could put together if we took a few minutes to do that. But for the sake of this video, I don't think I want to take the time to just do simplification. I really wanted to go over the concept of plugging back in and then just cleaning it up a little bit by multiplying by that denominator. And that tends to happen in these problems because they tend to end up with a quotient in the final answer. Hopefully that was helpful. Kind of hard, kind of difficult, but that will be it for this particular problem. All right, I'll see you back in class. Bye-bye.